Hello everyone, this is your homework for simplifying radicals. Unlike homework 3 as assignment, which you only needed for 2 different sections, you can see here that you need it for a lot more sections in your pre-calculus class. So it's going to make your life a lot easier if you master simplifying radicals in this course. So before we go over simplifying radicals, we need to go over some vocabulary first. We're going to be talking about the index a little bit, but we're really going to be talking about the radicand. Your index is whatever number is on the outside of your radical. So for example, if you have something like a cubic root, your index is a 3. If you have the fourth root, your index is the 4. We're going to be only focusing on square roots. And so square roots don't have a number here, but there's a known 2 to be there, right? Square root it's known to have a 2 there. You just don't see it. Just like when you have x, that's technically x to the first power, right? But we don't write that. Same thing with square roots. If you just see the radical, then there's a known 2 to be there. And then whatever is under that square root or that radical, sign is considered the radicand. Now, we need to know about square roots and stuff because just like addition and subtraction are opposite operations, you have multiplication and division are opposite operations. The opposite of squaring a number is to take the square root of a number. So that's what this is showing you right here, that they work backwards. So that's why whenever you do something like 8 squared is 64, when I take the square root of 64, that equals 8. And the reason is because 8 squared gives me 64. They undo each other. Okay, it works the opposite way. The square root of 36 is 6. Why? Because 6 squared gives me 36. Now you have something called perfect square roots, or perfect squares. Let me kind of fast forward to this next page. You have your perfect squares here, all listed. 1, 4, 9, 16, 25, so on. These are all perfect squares because they come out of that radical as whole numbers. But what happens if you have a number right here in between? What happens if you have the square root of 20? Well, if you put the square root of 20 in your calculator, you're going to get some decimal because it doesn't come out nice and pretty. However, there is a way to kind of simplify that, and that's what we're going to be focusing on. So it says here, it is possible to simplify some radicals that do not evaluate to rational numbers that, aren't perfect squares. But to do so, we must use the product rule for radicals. So the product rule says if you have the same index here, then you can multiply whatever's under the radical together. So in example 1, you have the square root of 10 times the square root of 7. Well, like we said, there's known 2's to be there, right? So I can multiply those together. We can call that the square root of 10 times 7. And so we can call that the square root of 70. Same thing here. You've got the same index. You got the cubic root. So we can say that's the cubic root of 25 times 3. So we've got the cubic root of 75. What we have to use to simplify radicals is this right here. But instead, it's almost like we're starting at where our answer is and going here to simplify it. Okay, we're breaking our multiplication up into factors. So there are 2 ways to simplify radicals. You don't need to master them both. Figure out which method is easier and master it. So we're going to go over the first method and then the second method here. I say here you don't need to master them both. I guess that's a little bit of a lie, and I'll show you why. But I kind of use both of them. If I can use method 1, I do because that's easier and quicker. but some of them, and I'll show you why, you're probably going to want to use method 2 because it's not as easy, it's not as obvious. So method 1, factoring out the biggest perfect square, and so that's why I have these all kind of listed here for you. If we had cubic roots and fourth roots and fifth roots and so on, we would need this information here. But technically, since we're only dealing with square roots, I don't really care about these perfect cubes, and I don't really care about my perfect fourths. Okay, just so we're clear on that for today. So, step 1, find the largest perfect square that is a factor of the radicand. So my radicand here is 200. And so I want to know the biggest number listed here that I can divide into 200. Well, I can't divide 144. I can't divide 121 into 200. But 100 does divide into 200. So we're going to start with 100. So this becomes, 200 becomes 100 times 2. And so that's our step 2 here. Write the radical as a product, right? I haven't changed anything. 100 times 2 gets me back to the square root of 200. Step 3 is to separate into 2 radicals. So this becomes the square root of 100 times the square root of 2. So notice I have literally done this right here backwards. Okay, we're just using the product rule, but in the opposite order. And then step 4 is simplify. Well, the square root of 100 is 10, and the square root of 2 does not simplify. And so my answer here is 10 square root 2. Okay, try again with 18. So I need to write this as a product with the largest perfect square. Well, I'm not going to start at, 25 doesn't work because that's too big for 18. So we'll start at 16. Does 16 divide into 18? No. What about 9? Does 9 divide into 18? Yes, it does. So this is 9 times 2, separated into 2 radicals. So this is square root 9 times the square root of 2. I now simplify. Well, the square root of 9 is 3. Square root 2 does not simplify. Now, I use method 1 when I can easily see, hey, 100 divides into 200. Hey, 9 divides into 18. But when I look at 48, it doesn't really jump out at me what perfect square jumps in. So something on 48, I might use method 2 down here. But for the purpose of this, we're going to go ahead and do it by method 1 as well. So 49 is too big, right? It's bigger than my number, so I can't divide 49 in. So we'll start at 36. Can I divide 36 into 48? You get 1.33, so no. What about 25? No. What about 16? Yes, we can. That's 16 times 3. So break it up. This is square root 16 times square root 3. The square root of 16 is 4, and then square root 3 does not simplify. Okay, so that's the first way to solve these, by finding the biggest perfect square. The second method is to use a factor tree. So says use the factor tree to find the prime factorization of the number under the radical. So what you do is you take whatever number you have, and so these are the exact same problems that we just did, right? We know the answer, but we're going to solve it this way. So you break this down until you get prime numbers. Does not matter how you break this down. Because we already broke it down as 102 here, let's do something different. And I'm going to break this down as 20 and 10. Break it down till you can't break it down anymore. So 20 is, let's go, 5 and 4. 5 is broke down, but 4 can be broken up to 2 and 2. And then 10 can be broken up to 5 and 2. So that's step 1. Step 2 says use the index to determine the group of factors. Because there's a known square on the outside, I need to group these up into 2's. So if this was a cubic root, I would need groups of 3. If it was a 4th root, I would need groups of 4. Okay, but it's square roots, we need groups of 2. So you find 2 of something. Well, I have 2 2's here, and I have 2 5's here. For each group, one factor leaves the radical. Whatever does not get a group stays inside. So 1 5 comes out, 1 2 comes out, and then this 2 here stays inside. Then we multiply the outside factors together. And if we had multiple ones on the inside, we would multiply those together as well. So my final answer, 5 times 2, gives me 10. Okay, let's try again. 18. We've already done 9 and 2, so let's do 6 and 3. 6 can be broken up to 2 and 3 can't be broken anymore. So find your groups of numbers. We have a pair of 2's. Sorry, we have a pair of 3's, right? Pair of 3's. So the 3 comes out, and whatever does not have a group stays inside. When I taught this in high school, I taught it as these 3's are going out on a date. So they're going outside the house. The 2 is lonely. He's staying inside. Okay, if that helps you. And if you notice, if we do break that down as 9 and 2, then you get 3 and 3. You still get the same thing. Your 3 comes out, your 2 stays in. So it does not matter how you break this down into prime numbers. And then 48. So again, we've already done this, right? But when I would look at this, I would say, I don't know what goes into this. I don't know what times what gives me 48, but I do know it's even, so I can divide in a 2. So 2 times 24, and now I can work with 24 a little bit easier. 24 is 4 and 6. 4 is 2 and 2. And 6 is 2 and 3. So what do we have a group of? I've got 2 2's and 2 2's. So what gets circled comes out, right? And only one of them. So 1 2, 1 2. And then whatever does not have a pair stays inside. Next, we're going to multiply the outside factors together. So my final answer is 4 square root 3. Like I said, it does not matter which method you prefer. just pick one. But I do use a combination. I would have used this method here, and I would have used this method for that one. But you can use them both for all of them. Okay? The last portion of this is your imaginary numbers. Before, when we would have something like the square root of 64, you can't have a negative under a square root, so you just say that's not a real number, and we can move on. Depending on where you are in pre-calculus, it's going to tell you about complex numbers or writing it in terms of I, and that's when you know you've got to use this information here. The biggest thing that we're going to be using is that I equals the square root of -1. You do need to know this one as well, that I squared is -1, but for this lesson here, you don't. So when you have a negative under that radical, you're going to take out that negative as a -1. So the square root of -64 becomes the square root of -1 times the square root of 64. We're using that product rule again, right? Well, the square root of -1 becomes I. What's the square root of 64? That is 8. And I times 8 is 8I. Now, if you can go straight from -64 to 8I, don't think you have to do all of these steps. Okay, but this is technically what we are doing when we get to 8I. Same thing here for square root -50. This is the square root of -1 times the square root of 50. Now 50 is not a perfect square, so we're going to have to break that one down. That should be a -1. So we've got the square root of -1 times, this one I know 50 is 25 times 2. That's an easy one. So square root 25 times the square root of 2. And so now simplify. This is I. This is 5. And I can't simplify this at all. So I times 5 times square root 2 gives me 5I square root 2. Okay, on C, square root of -72 is the square root of -1 times the square root of 72. 72 is one that I don't really know all the multiples for. So let's just start breaking it down. I do know I can divide, actually let's do it this way. I do know I can divide into 3 because 7 plus 2 is 9. So 72 divided by 3 gives me 24. And now I can work with that. That is 6 times 4. That is 3 and 2. And 2 and 2. I've got a pair of 3s and a pair of 2s. And let's not forget our I right here. So I've got 3 times 2 times square root I And then this 2 here is staying inside. So my final answer is 6i square root 2. Okay, now if you like that other method, you could have called, you could have called the square root of 72 as the square root of 36 times the square root of 2. The square root of 36 gives you the 6. All right. And then the last thing here, we have complex numbers. Complex numbers is a number. Excuse me. Complex number is a number that can be written in the form of a plus bi, where a and b are real numbers. So you would have something like 4 plus 6i. You've got your real component and your imaginary component. We have technically been dealing with imaginary numbers our entire lives, because you can also write something like 10 is the same as 10 plus 0i. Okay, those are the same thing. So, just like though, when you have something like this, that does not become 10i. If you have something like 4 plus 6x, you can't combine them, right? Because they're not like terms. Same thing with an imaginary. You can't combine when one's real and one's not. So really, these are all the exact same thing that we've been doing. It's just now you have a number in front that carries down with you. So I'm only going to focus on this part for right now. The square root of negative 20 is negative 1 times 20. The biggest perfect square that goes into 20 is 4. So this is negative 1 times the square root of 4 times the square root of 5. So we get I times 2 times the square root of 5. So I've got 2i square root 5. And then all you are doing is bringing that number in front, that component, down. And so this is your answer. You're going to get answers like this when you start doing the quadratic formula. Okay, I'm just going to focus on this part again. This is the square root of negative 1 times the square root of 98. This is one I don't know my multiples for. So I'm going to break this down. I know it's even, so a 2 will go into it. 98 divided by 2 is going to give me 49. 49 is a perfect square because that's 7 and 7. So my pair comes out. So I've got 7. My square root of negative 1 is my I component. This 2 stays under the radical. And then bring down that 17 minus. And then C. I am focusing on this part here. So this is the square root of negative 1 times the square root of 31. 31 is a prime number. The only way to get to 31 is 1 times 31. So that means it can't be broken down at all. So my answer here is 9 plus I square root 31. Not every single number in a radical can be simplified. Okay, if you have something like the square root of 19, that's just the square root of 19. You can't do anything with it. There's not a perfect square that goes in. All right, that's all I got for this lesson. You don't have any homework problems over this, but I cannot stress how important it is for you to learn this and get good at it, because you're going to have to be doing some other stuff. Like when you're doing the quadratic formula, you've got a lot of other stuff, and this is just simply the last step in the quadratic formula. So if you get good at this, it's going to make your life easier as this course goes on. Let me know if you have any questions. You can email me, or we can schedule a Zoom appointment.